Okay, so welcome, and today we're going to start talking about arc length and how do we calculate arc length. So one of the things that we're going to talk about is a lot of the applications before this, we've always required that the function be integrable, okay, or continuous. Well, when we're talking about arc length, we're going to have to be a little bit more stringent on what our requirements are going to be. So what we need to make sure is that the function must be differentiable, okay, at every point within the interval. And also the derivative of the function must be continuous. And we call this a smooth curve, okay, the smooth curve. So there must be differentiable, the function must be differentiable, and its derivative must be continuous. And again, that quality or the characteristic that we call is smooth. So now, what we're going to do is we want to estimate the length of this curve. Okay? So what we're going to do is we're going to estimate by using these segments, these line segments. So we're going to partition the interval from A to B. So let's say we have a closed interval from A to B. And so we're going to subdivide into regular intervals from, let's say, x0 to x sub 5 in this case. So that gives us 1, 2, 3, 4, 5 line segments. And so what we're going to do is we're going to use these line segments to estimate the length of the curve. Obviously, it's not going to be exact because we're using straight line segments instead of the curve. Okay? But again, we're going to use this as a starting point. So what we're going to do is now, so we've got x0 to x sub 5 from A to B. And so what we're going to do is we see that the height of each one of these points is f of x0, f of x1, and so on. So here's what we're going to do. We are going to find the length of these line segments. And in order to do that, we're going to create triangles, right triangles. So what we're going to do is we are going to find the vertical distance and the horizontal distance of these triangles here. And then we're going to do the same thing here. And here. And here, right? So now what's the vertical distance here? Well, here, this is going to be, since these are all regular subintervals, each one of these are going to be delta x. Okay, so we know that this is going to be delta x. Now, here, the vertical distance is going to be what? It's going to be the difference between f of x0 and f of x1. Here it's going to be the difference between f of x1 and f of x2. So we're going to calculate the value of this by saying that this is going to be f of x I minus 1 minus, well, you know what? Let's just put the values in here. So this is going to be f of x0 minus f of x1. This vertical distance is going to be f of x1 minus f of x2, and so on. Okay? And so that's what we're using. So we're basically taking the change in x over the change in y. So again, this is change in y. Oops. Change in y, so basically we've got change in x with the change in y for each one of these. Okay, so now we're going to use the Pythagorean Theorem. So so in general, let's set this up. Let me write it here. So we've got the length, okay, if we use the Pythagorean theorem, we've got delta x, delta y. So by using the Pythagorean theorem, we can get this distance is equal to the square root of delta x squared plus delta y squared, right? So we're just using the Pythagorean theorem to get each one of these hypotenuses. Now, we can rewrite this. So if I rewrite this, and again, I'm going to show you what I mean, is we're going to take this and I'm going to multiply the top and the bottom by delta x squared. Okay, so what I'm going to do is I'm going to leave this delta x squared here, and I'm going to distribute the denominator across here. So that what I get is this. I get delta x quantity squared times delta x quantity squared over delta x quantity squared plus delta y quantity squared over delta x quantity squared. Now I didn't do anything because all I'm really doing is multiplying through by 1. I'm just multiplying the radicand by 1. So I'm changing the way it looks, but I'm not changing it fundamentally. So now what I'm going to do is I'm going to pull this out of the radical because I can take the square root of this and I'm going to pull it out and say square root of x, okay, or I mean delta x, and then what's left inside I'm going to simplify and I get what? This becomes 1 and this becomes plus delta y over delta x quantity squared. So I'm just rewriting it then. You'll see why in a moment. So now, what I'm going to do is I'm going to pick a sample point. Okay? X sub I star for each subinterval. Okay? Let me make sure, I want to make sure I'm not missing anything. Okay, yeah, I'm good. Okay, so now what I'm going to do here is use the mean value theorem. So the mean value theorem says that on every one of these subintervals, there exists an x value such that there's some point, right? So there's some x value in this subinterval such that the tangent line of the f of x is going to be equal to the slope of this secant line. Okay, so let me repeat that. The mean value theorem says that, hey, if I'm connecting these two dots with a secant line, then the mean value theorem says there must be some x value, let's call it x sub I star, such that the derivative of x sub I star, so the derivative of the function evaluated at f of x, or evaluated x sub I star, is equal to this delta y over delta x. Okay, that's the mean value theorem. So what I'm going to do is I'm going to use that. I'm going to replace this because, again, since I know that there's got to be a tangent, a point where the tangent line is parallel to the secant line. That's what the mean value theorem is saying. Okay, so I'm going to use that. I'm going to substitute this into my formula. So this now becomes delta x times the square root of 1 plus f prime of x sub I star squared. Okay, so we got that now. So now, let's add up all these lengths. So this represents, right, so each star, we can figure this value out for each subinterval. And so then we can add them up. So the approximate arc length, let me write it down here. The arc length is going to sum up all of these values from x sub I 0 to x sub I, or excuse me, x sub I 1 to x sub I 5, because we're going to go from 1 to n. So now, that's going to equal the sum. Oh, let me use a different marker. That's going to equal the sum for x, x sub, no, I. So I equals 1 to n of the square root of 1 plus f prime of x sub I star squared, and then I'm going to put the delta x in the back here. Okay. Now, again, just like we always do, let's take the limit as n approaches infinity. And so what that's going to give us is, this is going to be the approximate arc length. Oops. But if we want the exact arc length, what we're going to do is we're going to subdivide these and start bringing these in closer, and we're going to get a more accurate measurement, right? Because these secants are going to get closer together, and we're going to basically go to infinity with the number of subintervals, just like before. And so what happens is now we're going to get the integral. So as n goes to infinity, so we're going to take the limit of this now. So arc length equals the limit as n approaches infinity of the summation from I equals 1 to n of the square root of 1 plus f of x of I star squared delta x. And now, what does this equal? This is going to equal the integral from a to b of the square root of 1 plus, now instead of x of I star, it just becomes f of x squared. Oh, I'm sorry, f prime of x. Sorry, I dropped the prime. F prime of x. So it's going to be the integral from a to b of 1 plus the quantity f of f prime of x squared, and then dx. And so that is going to be the integral that we're going to use for calculating arc length. And that's it. Have a great day.